Hi everyone and welcome to the internet. What we're going to be doing in today's chemistry lesson is having a look at carbon allotropes. So hopefully by the end of this lesson you're going to be able to describe what on earth we mean by the phrase carbon allotropes first of all, and then also explain the different properties that they have. To start off though, we've got 3 questions based around our previous lesson, so have a go answering those 3 questions in your books. So question 1, 3 marks available. 1 if you said it's arranged by atomic number, 1 mark if you said the elements are arranged in groups, and 1 mark if you said they're arranged in periods. Question 2, you can have any 2 of the following. He left gaps for undiscovered elements, he swapped iodine and tellurium around, and he organised the elements into vertical groups. So up to 2 marks for that one. And then finally, for question 3, group 0 are unreactive, and so they used to think that elements had to react to be an element. So add up your scores, it's a total out of 7 today. Let's start off with some basics about carbon then. So what we've got are 4 sentences on the screen. You need to write down these 4 sentences and have a go at filling in the blanks, and I'd suggest you look at a periodic table to help you out with this. So 4 sentences in your book, fill in the blanks as best you can, and we'll go through these. So I'm going to give you about 3 minutes to do this. Let's make sure we got the right missing bits in the right places. Obviously tick any you've got right, anything you got wrong, make sure you write the correct answer in. So carbon is in group 4 on the periodic table, and that means it's got 4 electrons in the outer shell, because if you remember what we've said previously, the group number tells us how many electrons there are in the outer shell. Because it's got 4 electrons in the outer shell, that means it can form 4 covalent bonds. So what we find is carbon can join with a range of other things, so other carbon atoms, hydrogens, other non-metals, etc., in order to make a huge range of compounds. It's an incredibly versatile element. So those covalent bonds that carbon can form can either be with other carbon atoms or with other elements. When we talk about an allotrope, then what we're referring to is different forms of an element that are in the same state, but they've got a different atomic arrangement. So what we actually mean here is that we'd be looking today at carbon. So these are all going to be these different structures made of only carbon atoms. They're all in the same state. The ones we're looking at today, they're all solid, but they've got different arrangements of those carbon atoms, and that then gives them very different properties to one another. So make sure you've got your definition of allotrope written down, so different forms of an element in the same state but with different atomic arrangements, and then see if you can answer the question underneath. What are the properties of diamond? I'm hoping that we came up with at least some of these properties of diamond. I picked out the most common ones if you like. So diamond is hard first of all. It's lustrous, which means it's shiny basically. Strong. It's got a high melting point and a high boiling point. It does not conduct electricity, and it's insoluble. So what we've got there are some of these key properties of diamond. And one of the questions they always used to like was they'd ask you why we use diamonds to make jewellery, for example. And you need to then back your answer up with these properties. So we'd obviously pick out the key ones for jewellery there. So something like lustrous, because it's going to reflect the light really well. You could talk about the fact it's insoluble, because there'd be nothing sadder than having a lovely diamond ring, washing your hands, and then, oh no, no diamond, it's just dissolved and washed down the drain. So you need to think about properties that make it good for a suitable purpose. If you didn't get those, obviously jot down any you didn't have, tick any that you did. The first allotrope of carbon we're going to look at in more detail, as you may have guessed from the question, is diamond. Now, diamond is a giant covalent structure, and it's made only of carbon atoms. And each carbon atom is joined on to 4 others. So if you have a look at the second carbon atom down in the diagram, then we can see that one there is joined on to 4 other carbons. You go to another one in the chain, you'll find it's joined on to 4 others. Now obviously that's just a small section of our giant covalent structure, so not all of them do appear to be joined, but in our diamond, each carbon atom is joined to 4 others through covalent bonds. Now, one of the things you could be asked to do is to recognise the structure of these different carbon allotropes. So I wouldn't suggest you necessarily try drawing that one with all the dots, but if you look at the general shape of it, it looks kind of like a triangle. So the easy way to remember the shape of diamond is with a little symbol of our triangle there. Now, once you've written down the top sentence and done your little sketch of a triangle, then I want you to have a go answering the question, why do you think diamond has a high melting point? And you need to use some idea about bonds in your answer. Hopefully what we wrote down is that diamond has a high melting point and is hard because there are many covalent bonds. Now, covalent bonds are strong bonds, and that means we need a lot of energy in order to break them. So anytime you get a question about something like carbon and having a high melting point, then the reason is there's a lot of strong covalent bonds that need a lot of energy to break them. So make sure you've got that sentence written down if you didn't get that correct. Next question, does diamond conduct electricity? Why? The answer is no, diamond does not conduct electricity, because remember, carbon has 4 electrons in the outer shell. It can make 4 covalent bonds. And in diamond, each carbon is joined onto 4 other carbons. So that tells us all of the electrons are being shared to form covalent bonds, which means we have no delocalized electrons. If there are no delocalized electrons, then current will not be able to flow through the structure. The second structure and carbon allotrope we need to know is graphite. Now, graphite is again a giant covalent structure, but each carbon atom is only bonded to 3 others. So we've clearly got a difference in how the carbon atoms are joined here between diamond and graphite. And the way it looks is the bottom left picture there. So what we actually have is those carbon atoms form these rings. The rings are joined together into sheets, and then the sheets are stacked one on top of the other. And what we've got strong covalent bonds between the individual carbon atoms, but those individual sheets, they've only got relatively weak intermolecular forces holding them together. So what we know then is if we've only got 3 covalent bonds, we've got this spare electron. So that becomes delocalized. So write down the first 2 sentences, do your little sketch there, and that one I always suggest as just a stack of lines on top of each other to remind you. And then answer the question, what property does this give to graphite? Hopefully what we got is that because we have a delocalized electron, then we can conduct electricity in graphite. Two more questions on the screen for you to have a go at answering. So first one asked about why a structure has a high melting point. Then we've got many covalent bonds which require a lot of energy to be broken. And the reason that graphite is slippery is because the weak intermolecular forces between the layers are easily overcome. So tick them if you got them right. Obviously, if you didn't, make sure you've got those 2 sentences written down.
The familiar gadgets of everyday life. They get faster, slicker, and slimmer. But an amazing new material, discovered by British scientists, will transform this technology forever. It will allow us to slim it all down to the thickness of a piece of paper. It's called graphene. Even under the microscope, it doesn't look much, but it won a Nobel Prize for the two scientists who discovered it, and it's been lauded as the miracle material of the 21st century. It's stronger than diamond, more conductive than copper, more flexible than rubber, and it's so thin you can barely see it with the naked eye. Graphene is made from the stuff in your pencil, graphite. And graphite is millions of microscopic layers of tightly packed carbon. When I put my thumb into the graphite, give it a rub around, it gets covered in a layer of it. And if I then press that back onto the paper, millions of layers are peeled off. If I keep smudging my thumb across the paper, these layers of graphite get thinner and thinner. And if I keep going, eventually I'll end up with a layer of graphite 1 atom thin, and at that point I've got graphene. Materials scientist Dr. Aravind Vijay Araghavan works with the team who discovered it.
This is graphene at about 20 million times magnification, and you can see the individual carbon atoms, which are the white dots you see here, and each carbon atom is connected to 3 other carbon atoms. Now the carbon-carbon bond is so strong that actually makes graphene 200 times stronger than steel.
To demonstrate graphene's properties, Aravind dissolves graphite, the stuff from your pencil, in a solvent, then injects it into a special printer cartridge. This sprays a thin layer of graphene onto a cellophane backing, which holds the thin graphene layer together.
What we have here then is cellophane coated with a layer of graphene.
You sure? Yes. Because it just looks like a piece of cellophane to me. On its own, cellophane cannot conduct electricity, but when graphene is added, something remarkable happens.
And we have an LED lamp there, and as soon as you wire it up, the lamp starts to glow, so which means that there is current flowing through a piece of plastic.
As graphene is so thin, there is very little electrical resistance, making it the most conductive material ever created, allowing scientists to shrink our circuit boards, leading to smaller phones and computers. But graphene has another key property: flexibility.
You can essentially pick it up and you can bend it and you can twist it, and still the current flows through it and the lamp stays on.
That is really quite incredible. This flexibility is getting electronics giants excited. Prototype animations show graphene applied to super thin bendy plastics, making phones and tablets foldable. So this is really revolutionary. This is going to change things, isn't it?
Yes.
Graphene's thinness also means it's 97% transparent, tackling a problem we face with touchscreen technology. Today's mobile phones contain an element called indium in the touch screens to make them work. It's rare and becoming more expensive, and the coating that it makes is brittle and inflexible. On the other hand, super bendy, conductive and transparent graphene is made from carbon, the 6th most abundant element in the universe. But high-quality graphene is currently hard to manufacture on a large scale. Any imperfections in the process dramatically reduces its conductivity. If scientists can crack this problem, it won't just be consumer technology that will change. Electric car batteries built from millions of layers of graphene will charge in minutes thanks to its high conductivity. Microscopic graphene sensors inside our body could detect harmful microbes, responding to tiny changes in conductivity produced by individual bacteria cells. Graphene may well be the biggest technological revolution since the silicon chip.
The third allotrope we're going to look at is graphene. Now, this one resembles a single layer of graphite. So where we said that graphite is multiple layers all held by these weak intermolecular forces, graphene is like we've just peeled a single layer off. Now, key things about this is extremely strong, it conducts electricity, and it's almost transparent, as we saw in the video. So suggest some of the ways that graphene could be used once you've jotted down those first two sentences. The next structure is the group called the fullerenes. Now, fullerenes are actually a whole family of carbon allotropes that have shapes that are either tubes or balls. So we've got nanotubes, which is basically like we've got a sheet of graphene that we've rolled into a tube, kind of like a straw. And we're going to use these nanotubes, and they're tiny things. Obviously, we're making these out of a single sheet of graphene. So if we've rolled that into a tube, it's still absolutely tiny, hence the word nanotube. And we use those to reinforce tennis rackets, and the reason we can do that is because they're really strong compared to their size, as we heard in the video. So jot down those three sentences for me if you've not already got them. The final allotrope we're going to look at is a buckyball. Now, a buckyball is basically carbon arranged into a sphere. So this is the one we're going to draw as a circle when we do our quick sketch to remind us. Now, buckyballs are really important because they're made up of 60 carbon atoms as the common one here. Now, what we find is that because it's a sphere, it's kind of like a cage. So what we can do is we can then put chemicals inside that cage, and we can then use it as a drug delivery system. So that means rather than having drugs that are going to be travelling, having effects throughout the whole body, this one would then be released in a specific region of the body to allow more targeted drug treatments. And we can also use them in things like lubricants as well. So jot down those couple of points about buckyballs for me. Final thing for today then are the plenary questions. So those of you with target grades up to grade 5, it's the two columns on the left. Those of you with target grades over grade 5, it's the two columns on the right. So I'll leave these up for about 3 minutes today, but as always, if you need longer, hit pause and take as long as you need to answer them.